Thank you, Pierre. Thank you, of course, to the organizers for the invitation, the chance to come speak here, and the chance to spend some time in Marseille again. Everything I will say today and in the second lecture tomorrow is joint work with Dan Thompson, who will give the last 3 lectures in this mini course next week. And I'll say a little bit more in a few minutes about how the material is divided and what the goals of the 2 weeks are. I should mention before I start that I put some notes on the wiki, so if you want to see more details, many things which I will omit during the talk itself, you can look there. That document will evolve because even since I posted it, I found some more things this morning that need correcting. So I will continue to change that, and eventually we hope to post a more complete survey article based on these notes, but, well, that will take some time to finish. So the idea is to say something about uniqueness of measures of maximal entropy, and then Dan will say something about equilibrium states. So maybe I better start by saying something about entropy just to remember the most basic idea. Suppose I have a probability vector. That is, I have n non-negative numbers which add up to 1. Then the entropy associated to this probability vector is the sum of negative pi log pi. And never mind why we consider this number. There are various reasons. This number is maximized over all probability vectors. Well, the maximum value is log n, and this is achieved if and only if all of the elements of the probability vector have equal weight. And this is a calculus exercise. It's not particularly hard. Of course, there's no dynamics in this, but this serves as kind of a motivating principle that there's this quantity called entropy. It's maximized at a unique point, and that unique maximization point has the property that weights are equidistributed across all possibilities. And those connections are ones which will come up over and over again through the remainder. But now I should say some dynamics. So the setting will always be the following. Let X be a compact metric space, and F a continuous map from X to itself. So we consider a discrete time system. Some of the examples I consider later will be flows, and especially the ones that Dan considers next week. All of the results that I state have analogous results for flows, but for simplicity, I'll state them for discrete time. Given a topological dynamical system like this, I will write M sub F for the set of all Borel F invariant probability measures. And if X is some set on which the system F has some hyperbolicity properties, then this space can, of course, be extremely large. For example, if it's the full 2-shift or subshift, transitive subshift of finite type, it's this infinite dimensional simplex in which the extreme points are dense. So it's this gigantic thing, this Paulson simplex. And it's an important question to understand what are the distinguished elements of this? What are the important invariant measures to study? How do we identify them? And one way, certainly not the only way, is to consider a measure of maximal entropy. So the variational principle says that the topological entropy is equal to the supremum of the measure theoretic entropies. I will not define measure theoretic entropy, but the full definition is in the notes if you need reminding. I will define topological entropy later, but not right now. So for the moment, you can take this as a definition of topological entropy. And the object that I want to study is a measure of maximal entropy. Which, since it takes a little while to write, I will always abbreviate to MME. Yes?
How do you know it's achieved?
If a measure achieves it, then it is called a measure of maximal entropy. So the fundamental questions are, does such a measure exist? And is it unique? And at this level of generalities, the answers are not necessarily and not necessarily. So if we want to say something about existence and uniqueness, you need more assumptions. You need to work with a more restrictive class of systems. So the fundamental classical result is that if X is a subshift of finite type, or if X is a locally maximal hyperbolic set for a diffeomorphism F, and if you add the assumption of topological transitivity, then it does exist and it is unique. So there exists a unique measure of maximal entropy in this uniformly hyperbolic setting. And there are multiple ways to prove this. The original proof, I guess, was that you have a Markov partition for such a set, so that reduces it to the case of an SFT. And for an SFT, you can construct the unique measure of maximal entropy using the transition matrix, and that's the construction of Perry measure. Another proof is available that uses some tools from geometric measure theory. This is actually a much more recent proof. Well, it has its roots in some work from Hammenstadt in the late 80s, and I think Boris Hasselblad has a paper about that too. And that has something to do with the talk that Agnieszka Zellerovich will give next week. But I want to spend the duration of my time talking about the approach via expansivity and specification. So this is a proof due to Bowen. And I will not say what these are immediately. Definitions will come in a bit. For the moment, let me simply say that these are two properties which are satisfied by transitive SFTs, by locally maximal hyperbolic sets. And I will spend today talking about how the specification property, what role it plays in the proof, and then telling you how it can be generalized to something weaker using the notion of a decomposition. Next time, tomorrow, I will say something about the role that expansivity plays and how you can weaken it. And then in the third talk on Friday, I will say something about examples. So the goal of these lectures is to generalize this result So generalize these definitions and then explain some applications. In particular, today I will mention the application to beta shifts, assuming that I get there in time. Next time I will mention the application to some derived-from-Anosov partially hyperbolic diffeomorphisms. And then on Friday I will describe an application to Bunamovich stadium billiard map and to geodesic flows. So that's the plan. Okay, very good, very good, very good. Okay. So I want to say something about how Bowen's proof works, first just in the symbolic setting. So let me consider this first case where you have a transitive SFT. More generally, I'm going to consider shift spaces, by which I mean that we fix a finite set A, which is the alphabet of the shift space. And I will consider one-sided shifts. Everything I say has an analog for two-sided shifts. And in fact, the proofs are nearly identical because they are all given at the level of the language. So I should say what I mean by the language. For that, I need to first say what X is. So X will be a closed shift invariant subset. That's what I mean by shift space. And so far, there are absolutely no assumptions beyond that. It's not necessarily an SFT or anything else that might be nice. We'll need to put some assumptions eventually. Given a finite sequence of symbols, a word, we can associate the cylinder, which is the set of all elements of the shift space, all infinite sequences over this alphabet which lie in the shift space, and which begin with the word W. I'll use interval notation in subscripts to simply denote the subword. So this means x1, x2 through xn.
So you have no x0, is that right?
I'm starting indexing at 1, yes. So, then we have a notion of the language. Ln, which depends on your shift space x, is the set of all words for which the length is equal to n, and the cylinder is non-empty. So this is simply all the words of length n which appear in some element of your shift space. And if they appear anywhere in the sequence, then after shifting them for a while, they appear at the start. And it's shift invariant, so this is the set. And then the language is the union of all of these. And I want to describe the proof at the level of the language of the shift space. This is going to be our kind of fundamental object. So I defined what I needed to define there. Very good. Okay. I guess I should also say that in this setting, one can give a nice, simple definition of the topological entropy. The topological entropy of the shift space, which I will usually abbreviate simply to h of x in the interests of brevity, is the limit, as n goes to infinity, of 1 over n log of the number of words of length n. So it's the exponential growth rate of the complexity of the number of words in the language at a given length. And it's a not too difficult exercise that's equivalent to the standard definition of topological entropy, which will come later. Okay. So that's the basic terminology and notation from symbolic dynamics. And now I want to outline how this proof of existence and uniqueness goes. And I will first say how you establish uniqueness, because that's the part of the proof that I'm not going to explain in any detail right now. And then I'll spend some time talking about the existence part. So to motivate the uniqueness, maybe it's helpful to start by recalling the Shannon-McMillan-Bryman theorem. The Shannon-McMillan-Bryman theorem tells you that if you have an ergodic measure, So an ergodic shift invariant measure. I'll put a superscript E there to indicate that I consider an ergodic measure. Then for almost every point, if we consider the cylinder corresponding to the initial segment, the initial word of that point, that measure decays exponentially quickly, and the rate of decay is equal to the measure theoretic entropy, and that's true for almost every point. So we can rewrite this a little bit in a way that may look a little unnatural. This says that minus 1 over n times log of the measure divided by e to the n, e to the minus n times the entropy. Converges to 0 almost everywhere. Okay, this is a funny way of writing it, right? I just made it look more complicated. The reason that I want to write it in this way is that this ratio, as a result of this convergence to 0, I can say that this ratio does not go to 0 or infinity exponentially quickly. So this is sub-exponential. And that's a completely general thing. It's true for every ergodic measure. Now suppose I strengthen sub-exponential just a little bit. Well, it's more than a little bit, but it doesn't look big. So here's the theorem. Now, let me call it a proposition since it's 1/2 of the proof of that theorem. The proposition is that if mu is a ergodic measure on the full shift with the property that there's some constant k for which this quantity not only does not go to 0 exponentially quickly, but in fact is bounded away from 0. And I'll write it in terms of k inverse simply because later there will be a two-sided bound where k is the upper bound and k inverse is the lower. Then it turns out that mu is the unique measure of maximal entropy for the shift space that is its support. So given any invariant measure, it's easy to show that the support of it gives you a shift space. It's closed by definition of support. It's shift invariant because the measure is invariant. And as soon as you have a measure with this property, so this is a lower Gibbs bound. Oh yes, thank you. The dependency is that, well, I want it for almost every x, and I want it for all n. But the almost every x is actually kind of a fiction here, because as soon as you have the uniformity, you get it everywhere. So, a very short argument shows that this condition actually implies that the measure of any word in the language of the support admits this lower bound And this is perhaps the more familiar form of this lower Gibbs bound. And this is the form that I'll use it in everything that follows. Yes?
Why is mu a measure on the full shift rather than on x?
Well, you can. Oh, because it's a proposition where I don't assume I start with some subshift. I just start with some measure. Now, in practice, every time we use it, we start with a subshift, and then I'm interested in constructing a measure for which this holds for every word in the language, and therefore it is fully supported on the subshift. So this proposition it's formulated in a little bit of a convoluted way from the point of view of the way we will use it. So let me reformulate it. I formulate it this way to try to highlight the analogy with Shannon, Macmillan, Bryman, which for me is a bit of the motivation of why some property like this is important. But let me formulate it the way that we use it. So the proposition is that if x... Sorry?
This is still metric entropy, just integrating the quality, right? The last line.
This one? It's a standard. It's sort of a routine argument with entropy to show that if you have this bound, then you do the computation of entropy for this measure, and it turns out it must be equal to this topological entropy. So this entropy must be equal to the topological. This is topological entropy. Yes. So let me formulate the general uniqueness proposition. If you have some subshift, and you have an ergodic, measure for which there exists a k satisfying this lower Gibbs bound, for every word in the language of x, then the measure is the unique measure of maximal entropy on this shift space. So this is the fundamental mechanism behind uniqueness. That in order to establish uniqueness, you should prove a Gibbs property. Well, you should build a measure of maximal entropy. You should prove that this measure is ergodic, and you should prove that it has a lower Gibbs property. And that's going to be the goal. In fact, once you know it has the Gibbs property, the fact that it's an MME follows. So, I will not say anything more about the proof of this proposition right now. I'll say a little bit more about it next time when I discuss the role that expansivity plays. But so far I haven't defined expansivity or specification, so maybe I'd better define specification. Because specification is the tool that will let us build a measure like this. So, it's a short exercise to show that if I have a transitive subshift of finite type, then it has the following property. Sorry. Get the quantifiers in the right order. First, there exists a natural number tau, which you can take to be the diameter of the graph that presents the subshift of finite type. And you have the property that for every pair of words in the language, no matter how long they are, there exists a word u that connects them and has length at most tau. So not too hard to verify this property for transitive SFTs. Of course, if I remove this condition on the length of U, then this is just the definition of topological transitivity. So it's sort of a uniform transitivity kind of property. And if I assume that the SFT is mixing, then I can actually get the length to be equal to tau, but less than or equal to tau will suffice for all of the results. By iterating this property, one concludes that for every collection of words, W1 through WK, I'll use superscripts on words to indicate different words and subscripts to indicate letters within a word. So these are K distinct words in the language. And by iterating this property, I can find K minus 1 connecting words, all of whose lengths are less than or equal to tau. And with the property that if I write all the words WI in order and put the UIs in between them, then I get a word in the language. So the idea is that this somehow mimics the property that the full shift has. Because if you're the full shift, then you can simply write down, take any sequence of words, write them down one after another, and you get another legal word. In a general shift space, you cannot do this. However, this property, which is the specification property, so if there exists a tau such that this second line holds, then we say that the shift space X has the specification property. And the way that Bowen proved this theorem in the case of symbolic spaces was to prove that if your shift space has specification, then there exists an ergodic measure mu which satisfies this Gibbs bound. And therefore, and then he proved uniqueness using the proposition that I didn't prove. So how do we build such a measure? To use specification to build an ergodic Gibbs measure. Well, if you ever look at the proof of the variational principle, you see there's a standard way to build a measure of maximal entropy. Or at least to try to build a measure of maximal entropy, and it works if your system is expansive, which symbolic systems are. So the general construction is that you start with a measure nu n for any n, and you can take this to be any measure that's equidistributed on words of length n. So it gives every word of length n equal weight. This is the natural thing to do. Remember the very first computation, right? If you want to maximize entropy, you should give everything the same weight. Now the problem is this is not an invariant measure, but we know how to build invariant measures, right? You start with any old measure in the world, you push it forward and you average and you take a limit point. That's the usual Krylov-Bogolubov construction. So we start with these measures nu n, and we consider the measure mu n, which is simply the average of the first n of these. Not the average of the first n nu n's, the average of nu n over the first n iterates. So you push it forward under the shift map, k times for each k from 0 to n minus 1, and you average those measures. And by push forward, I of course mean that you compose it with the preimage of the shift map. And then it's a very completely standard argument that any limit point of this sequence, and limit points exist by compactness, is invariant And one can do a computation that proves it's a measure of maximal entropy. In fact, we will not need that computation right now because we're simply going to prove the Gibbs property directly. Or at least I'll show you the outline of that proof. So the claim is that if X has specification, so if I have a shift space with the specification property, and I do this standard construction of the MME, of a MME, then any such mu is ergodic and has the property that there exists a constant k such that k inverse times e to the minus n topological entropy of X is less than or equal to the measure of a word, is less than or equal to k times e to the minus n topological entropy of X for all words of length n. Yes?
This measure mu n that we define as a mu n, the number n, the index n in mu n, should be independent of mu n?
I'm sorry? Here?
Yeah.
Yeah, I mean, the standard argument that you referred to has a nu, not a nu e.
Okay, yes, sure. The standard construction of an invariant measure in the proof of Krylov-Bogolubov starts with a single measure and pushes it forward. But the proof works just as well if you do this. So yes, you're right. It's a slight modification of the standard argument. But I do want to start with a different measure each time.
What if you have two sequences, one goes to infinity, these two together?
Where?
No, you have two n's, right?
Here and here?
Yeah, what if n is 2 to the n, or I don't know, n squared or something?
I mean, then you're simply putting a different sequence of measures here.
Yeah, but will it work?
You still get an invariant measure. Now, whether you get an MME, it depends what you want it to work for. I want it to work to get a Gibbs property, and so I think it's important that they be the same. I think it's quite important that they be the same.
In this approach, it doesn't matter that your mu n was a measure distributed uniform. Just take anything.
Right. This will give you an invariant measure no matter what sequence you start with. Yes, it's a completely general thing. So now I need to say how we get the Gibbs property. So Gibbs property and ergodicity. So there are two main steps to this proof. And this should go all the way up now. And the first step is to prove some counting bounds. There's a general principle at work in the uniqueness argument, which is that in order to get good uniqueness results, Gibbs measures, etc., we want to take a quantity which behaves sub-exponentially for very general reasons and prove that in our specific case, it actually is bounded. The Gibbs property is one manifestation of that. The counting bounds are another, now using the number of words of length n. So let me explain what I mean by that. There's a very natural map from words of length n plus k to the set of pairs of words, one of which has length n and the other has length k. You just take a word and you write down the first n letters and then you write the next k. And this is 1-to-1. Therefore, the number of words of length n plus k is less than or equal to the product of these. So from this, you then deduce that, in fact, so if you iterate this iterate this a number of times, you get that the number of words of length k times n is at most the number of words of length n to the power k. And then I take some logarithms. So I take log of both sides and divide by k times n. And I get that this is less than or equal to 1 kn. No. 1 over n. So that's a very short computation. And now as I send k to infinity, the left-hand side converges to the topological entropy. Whereas the right-hand side is completely independent of k. And that immediately implies that 1 over n log number of words of length n is greater than or equal to the topological entropy of the shift space, which we can rewrite as the bound number of words of length n is greater than or equal to e to the n times topological entropy. And I used nothing about the shift space, right? I did not use specification. This is a fact which is true for any shift space. Now I want an upper bound. For an upper bound, I need specification. So the idea is that using specification, I can get a map in the other direction. If you give me a word of length n and a word of length k, then I can put them together. Now I have to insert something in between. But the thing I insert in between is of length at most tau. So I get out a word of this length. Okay, there's some irritations here because I only required the connecting word to be length less than or equal to tau. So maybe I need to add some symbols at the end. And the map is not necessarily one-to-one. But it's close to one-to-one. I have an upper bound on the multiplicity, and so by doing a similar argument, I conclude that the number of words of length n is less than or equal to some constant times e to the n times topological entropy. So the counting bounds that I obtain are that e to the n entropy is less than or equal to the number of words of length n is less than or equal to a constant times that. And to reiterate what I said a couple minutes ago, if you look at the definition of topological entropy, it says that the ratio between these two quantities is sub-exponential, because if it wasn't, the entropy would be something else. And these bounds say that not only is it sub-exponential, it's actually bounded away from 0 and infinity. So it's another manifestation of this phenomenon. So those are the counting bounds, and that's the first part of the proof. The second part of the proof is to establish the Gibbs property. So if you want the Gibbs property, you need to go back to how the measure was actually defined. If I leave it there, it's more visible. So how was the measure defined? The measure was defined via these measures nu n. So I need to estimate. So step 2 is Gibbs and ergodicity. And in order to prove both of these, the idea is to estimate this quantity. Because the measure mu n was defined by averaging measures nu n composed with sigma minus k. So if I get a good uniform estimate on this bound, then averaging over all k will give me a good estimate for mu n, and that will be my Gibbs bound. But these measures are defined so that every word of length n has equal weight. So if I want to know what that weight is, I simply look at all words of length n, and the number of such words is, well, cardinality of ln, which I have very good estimates on. Now I want to know how many of those have a W in the kth position. Well, here there should be a word of length k. And here there should be a word of length n minus k minus the length of w. And the same argument as in the first step of the counting bounds says that the number of words which have a w here is at most the number of words of length k times the number of words of this length. So this measure is less than or equal to the number of words of length k times the number of words of length n minus k minus length of w divided by the number of words of length n. I have good estimates on all three of those quantities. So this is less than or equal to q times e to the k times entropy times q times e to the n minus k minus length w times entropy, all divided by e to the n times entropy, where for the denominator, of course, I need the lower bound on ln. And now things simplify, and this is q squared times e to the minus length of w entropy. Well, that's exactly an upper Gibbs bound. To get a lower Gibbs bound, you make a similar argument, but instead of saying that for every such word you have a unique pair of words here, you go the other direction and you use specification. So you say that you can put any word here of length, well, not quite k, but k minus tau, because you have to allow some space to glue. And you get similar lower bounds via a similar argument. And so the conclusion, so we get the Gibbs bounds, which I stated up there. So that's one half. And the next half is to prove that the measure you get is actually ergodic. So where does ergodicity come from? Well, ergodicity comes from a very similar argument. The first step in the proof of ergodicity is to show that if instead of having a single word here, I want to have a word v here and a word w somewhere else, then I can do similar arguments as long as there is enough space between them. And I want to argue that the Lin sup, as n goes to infinity, of the measure of a set like this is greater than or equal to some constant times the measure of the two cylinders. So it's a partial mixing property. So here C is some constant independent of V and W. You want this to be true for all words V and W, regardless of their length. And the argument, as I say, is essentially a recapitulation of the lower Gibbs bound, just with more estimates. But once you have this property, then you can use the fact that cylinders generate the Borel sigma algebra. And you have a uniform bound here. So because cylinders generate the Borel sigma algebra, you get the same estimate for any measurable sets V and W. And that implies ergodicity by simply considering the case when V and W are the same set and that set is invariant. Okay, so that's the outline of the proof of Bowen's result. Now, what time do I need to finish? 10 minutes, okay. So now I have 10 minutes to tell you. Okay, I have 5 minutes to tell you how this weakens via a non-uniform specification property.
Can I ask a question? Maybe the upper and lower bound, but it looks to me that you put the upper bound.
Yes.
That's not the one which gives uniqueness.
Correct. I skipped very quickly over the fact that you also get a lower bound. That's where you use specification, yes. The lower bound, it's a more complicated looking estimate, so I don't want to write it. But it's this general principle that you have a correspondence between words of length n and pairs of words of shorter lengths. So how do we do this with some non-uniform version of specification? Well, let me change my definition of specification in a very minor way. So specification originally said that I have a gap length such that I can concatenate any finite sequence of words using connecting words shorter than tau. I'm going to weaken this in the following way. I'm going to say that a subset G of the language has specification if there exists some gap size tau such that this property is true provided all my initial words came from G. That's it. That's the modification. So I think of this as a collection of good words. Now, of course, a priori, this is an extremely weak property because I could take like the empty collection or something. So I need something to guarantee that my collection is large. The way that I will guarantee my collection of words satisfying the specification property is sufficiently large is via the notion of a decomposition. So a decomposition of the language is a choice of 3 collections of words.
Sorry, I missed something.
Yes?
So you change L by J just at the first and then...
Only at the first. I do not require that this be in G.
Sorry?
This is not required to be in G. These are not required to be in G. Only the words that I start with. So a decomposition of the language is a collection, 3 collections of words. I think of these as prefixes. I think of these as good words. And I think of these as suffixes. And this should have the property that for every word in the language, there's a prefix and a good word and a suffix, such that when you put them together, you get your original word. So that's a decomposition. It's a collection of, you need a list of suffixes, a list of prefixes, such that starting with any word, you can remove a prefix, remove a suffix, and get a good word in the middle. I need 2 more definitions, and then I can state the theorem, and then I will be done. So the definitions I need are that for an integer capital M, GM will denote the set of words in the language for which these prefixes, the corresponding prefix and suffix, are both shorter than M.
Was there any uniqueness between
No.
US?
I'm not requiring any kind of uniqueness. One word could have multiple different decompositions.
So at this point, it's
If-
existence of
It's just existence, it's just existence of a decomposition like this.
with the things short.
So for GM, yes, it's just the existence of UP and US, which are short. Yeah. So and you should think of this in some sense as being like a family of Pessin sets, because the union of all of these is the language, the union over all M. And I'm going to ask for each of these to have good properties. So here's the theorem. Suppose I have a shift space which admits a decomposition with the following properties. First, each of these collections GM has specification. As you increase M, the gluing time can increase. So tau is allowed to depend on M, but that's it. And second, I need the prefix and suffix collections to be small. So I need their entropy to be smaller than the entropy of the whole thing. I'll make that definition in 10 seconds. The conclusion is that then there exists a unique MME. And when I write H of the union of prefixes and suffixes, if D is a collection of words, then H of D is just the thing over there. It's just the exponential growth rate, except the limit may not exist. So let me take an upper limit. So I look at the set of prefixes and suffixes of a given length, and I look at how quickly that grows. If the exponential growth rate of the prefix-suffix collection is smaller than the exponential growth rate of the whole language, then they are small enough that they are invisible to Bowen's proof. So then the idea is that one can run Bowen's proof, and if you want to see some of the details of how that works, you can look in the notes, but I'm out of time, so I will end there.
Any question? So wait for the... Please.
Use this for... So this is well adapted to the situation when you have symbolic dynamics.
Yes.
If you go to smooth dynamical systems,
That's tomorrow.
where you may or may not have symbolic representations, and then you have to redo the whole theory to kind of specify it for for smooth but not necessarily uniformly hyperbolic systems.
Well, in the smooth setting, there's a dictionary. The dictionary is that to the language, in place of anything that involves the language, we work with the space of finite length orbit segments. And so by this I mean that a pair xn corresponds to the orbit segment of length n beginning at x. And everything here that is stated in terms of language admits a translation directly into this domain, and then the similar theorems are true. And that's what I'll talk about tomorrow.
Any other question? So let's thank the speaker again.